All right, so 5.1, key features of exponential functions. Just looking at a comparison, kind of more as a reminder on what are the differences between linear, quadratic, and exponential functions. So starting off with linear, we're going to look at the table for this function that's graphed here. A linear function is any kind of function that takes on the shape of a line. Oftentimes we write it as y equals mx plus b. It's the easiest way to graph from, where m is the slope and b is the y-intercept. Whenever I have a function that's kind of centered around the origin, I usually pick these values for x to start at. They work out pretty good for the most part. They can always be adjusted. They can always be different. I could get these tables from a graph. My graph here is a little bit not perfectly precise. I could also get it from plugging into a function if I was given a function. For all intents and purposes, I'm just going to go ahead and write down the coordinates that I was expecting to hit on this graph. Oops. There. 1, -1, -3. And when we look at looking for patterns in a table, the pattern for a table of a linear values is when I look at y, I'm going to have some kind of a common difference. So what is the difference between one y value and the next y value? From 5 to 3, I would subtract 2. From 3 to 1, I would subtract 2. From 1 to -1, subtract 2. That common difference, if I have a table where the x values change by 1 and the y values have a common difference, that's indicative of, oh, I could identify that as a linear function. Key difference for a quadratic function is that the highest term in the polynomial is going to be ax squared. When a is positive, this opens up. And when I look at some coordinates here of a quadratic table, quadratic function, they may look like this. I were to look at differences in a quadratic function, so here I subtract 3, I subtract 1, I add 1, and then I add 3. The first difference is not the same. But if I do the second difference, this is adding 2, adding 2, adding 2. Now I get a common number. Quadratic functions always have a common second difference. And our focus on this unit is going to be looking at exponential functions. We'll be looking at parent functions and how they change as we have transformations. So for the graph above, when I plug in -2, I would actually get 1/9. I plug in -1, I get a third. Plug in 0, I get 1. Plug in 1, I get 3. Plug in 2, I get 9. Now, if I go through and I look at these y values and I try to find a common difference, doesn't matter if I do first difference, second difference, third difference, you're not going to find anything. So if I were to add here, I think, let's see, 1/9 to 3/9, I add 2/9 here, and then here I add 2/3, and then here I add 2, and here I add 7. And if I look at the second difference, it's not going to be common either. What does change here with an exponential function is this is actually what's called a common ratio, because I'm going to multiply by a number. So to get from 1/9 to 1/3, I would multiply by 3. To get from 1/3 to 1, I would multiply by 3. To get from 1 to 3, I multiply by 3. And then 3 to 9, I multiply by 3. Oops, I said 3. All right, key features of exponential functions. Whew. So we're going to graph y equals 2 to the x. This is a parent function with a base of 2. parent exponential function is always going to be of the form f of x equals b to the x, where b is some number, some real number. In this case, we're doing base of 2, but I could have a different number in that 2 spot. We're going to make a table, draw a graph, and then look at a bunch of the key features. I'm going to choose to not use a calculator here. If you want to practice using a calculator to kind of get this, I don't know, really dialed in, that's totally fine. I'm going to plug these in by hand. So I have y equals 2 to the x, and my first x value that I want to plug in is negative 3. So when I plug in 2 to the power of negative 3, we have to know what that negative exponent does. So a negative in the exponent is going to cause me to take the reciprocal of this and write it as a positive exponent. So instead of 2 to the negative 3, I have 1 over 2 to the positive 3. Let me write that a little bigger. I feel like this screen is very small today. And 1 over 2 to the positive 3, 2 cubed is 2 times 2 times 2, which is 8. So I have 1/8 for my y value. So when I plug in the next negative exponent, 2 to the negative 2, well, I never want to have a negative in the exponent, so I'm going to rewrite that as the reciprocal. 1 over 2 to the positive 2. 2 squared is 4, so I get 1/4. Same pattern, 2 to the negative 1 is 1 over 2 to the first, so that's just a half. Two to the power of 0. Anything to the power of 0 is always 1, so not a lot of figuring there, just got to remember the rule. And when the x value is 1, if I have 2 to the first, that's just 2. 2 squared is going to give me 4, and 2 cubed is going to give me 8. My boxes are really tiny. I'm going to choose to use 2 boxes to equal every 1 unit. You may want to do yours differently, and that's totally cool. Let me take a minute to get this dialed in. Nope. Like I said, you might choose to just use one box equal to 1. That's totally fine. My boxes are really small on this screen. So I'm going to use 2 boxes is equal to 1 unit to make sure that this graph is not too tiny for you to see. Okay, go ahead and plot those points. -3 up an eighth. -3 up a quarter. Let's see, that's 1, that's a half, that's a quarter. -1 up a half. 0, 1. Make sure you're not just counting my boxes unless you're using the same scale I am. 2, 4, 3, 8. So one of the defining features of an exponential function is it will always get bigger faster than any polynomial function. So as in this case, as x gets bigger, y is going to shoot up really, really high. We have different ways that we can describe domain and range, and we flip-flop back and forth in this class a lot. We're going to describe it today in the terms that you're going to see on your Savas homework. All right, so when I look at the domain, as I look to this graph to the left, and as I look to this graph to the right, there are no barriers. There's no asymptotes, there's no holes, there's nothing stopping the graph. The graph's going to go forever to the left and forever to the right. So we can write that as all real numbers. We've also seen this written in interval notation and inequality notation. So these all have the same meaning if I were to write it from negative infinity to infinity, whether I use parentheses or whether I use inequality symbols. So all have the same meaning. Now the range is not going to be all real numbers. As I look the graph up, it goes on forever and ever and ever. But as I look down, on the left-hand side of this graph is going to get closer and closer and closer and closer to the x-axis, and it's never going to cross it. Right? So I have this asymptote here. In this case, it's on the x-axis. I'm going to draw that in. And this asymptote in this case is on the line y equals 0. That is going to shift if the graph moves up and down. But in this case, it's here. Well, that determines my range because my range is going to come down. It's going to get really, really, really close to this asymptote, but it's not going to cross it. So for the y values, I come down and I don't quite hit 0, but I get close to it, but I do shoot all the way up. So the range can be written in different ways. If I were to write that in interval notation, I would write from 0 to infinity. If we were to write that in inequality notation, it would look like y is greater than 0. The homework in this case uses set notation, so let me show you how that looks slightly different. So if you remember, set brackets are like these kind of crinkly, curly brackets. So the range is y such that y is greater than 0. So really, we're just utilizing interval notation, but it uses some brackets there. And if you get confused on Savas, it'll give you a hint. All right. So the range is the y values such that y is greater than 0. The y values, this line here, would just mean such that y is greater than 0. Which is really not that different from this notation. And I don't know why they're asking you to look at it from another perspective, but just so you're not shocked when you see it, it's the same thing. All right, the intercept in this case is just the place where the graph crosses the y-axis there. A lot of times in this class when we talk about intercepts, we want the coordinate. In this case, we're going to give just the integer value. So the intercept's at 1. And then let's talk end behavior. So when we look at exponential functions, this is the first time where we don't have functions that are going to infinity and negative infinity in every direction. So this actually is going to look a little bit different. The structure of writing in behavior is the same. Let's see. As x goes to something, y goes to something. As x goes to something, y goes to something. The right-hand side is going to feel more familiar. So as I look to the graph to the right, as I follow this graph to the right, to the right, to the right, to the right, as x gets bigger, as x goes to infinity, what happens vertically? Well, this shoots up to positive infinity, right? So the right-hand side, as x gets bigger, y gets bigger. So we call that as x goes to positive infinity, y goes to positive infinity. But on the left-hand side, I get this whole leveling out action going on with the asymptote. So as I go to the left for the x values, right, these exist all the way over here. I can go left, 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 left forever. But what happens vertically is it does not shoot up or shoot down. It actually levels off right here at 0. So this is a little bit different phenomenon. As x goes to negative infinity, y goes to 0. It doesn't shoot up to positive infinity, doesn't shoot down to negative infinity. It levels off at the asymptote. If there's an asymptote, and there always will be for an exponential function, that's going to go on one of the y values. It doesn't have to be the second one. It could be either one. Phew. Okay. So now taking a deep dive into transformations of parent functions. And really looking at all of the meanings behind that. Take a moment to copy that down. Okay, so going over this, you've seen this so many times this year, but always different for a different family of functions. So the parent function is what's written in black. So y is equal to b to the x is going to be the parent function, or b can't be 0 or 1. The things that cause transformations, if I multiply by a, I get a stretch or a shrink. If a is negative, it's a reflection. Now, it's a stretch when a is a number greater than 1. It's a shrink when it is between 0 and 1, when it's like a fraction or a decimal or something like that. Whatever I subtract inside the parentheses to my argument, x minus h, is going to cause a horizontal shift. So if this is a x minus 2, that's going to be to the right 2. And if it's a subtraction, then it's actually going to be, no, if it's a subtraction, it's going to be to the right. If it's an addition, it's going to be to the left. It's always the opposite. Whatever's in those parentheses that I do to x is always going to be move horizontal, and it's going to be the opposite of what you would normally naturally think. And then the vertical shift is whatever I'm adding outside the argument. So any positive number is going to cause a shift up, and negative number is going to cause a shift down. When b is greater than 1, so looking at the parent function, when b is greater than 1, that's an exponential growth. That's like the example that we just did. B was 2, so that increases by 1, or it's an exponential growth. And if b is less than 1, like if it's a half or 0.3, then it causes an exponential decay. All right, we're going to look at 2 more examples in depth today. And then we're going to save the application problems for next time. So example set 1, we're going to look at the graph and identify the domain, range, intercept, asymptote, and end behavior. All right, so y is equal to 3 times 1/2 to the power of x. First thing first, I want to identify, is this an exponential growth or is it an exponential decay? So my parent function is y equals 1/2 to the power of x, and the 1/2 is going to be what determines that this is an exponential decay. So this is going to go in the opposite direction. Exponential decay means it's going to go, I'm going to have a decrease as time goes on. First thing first, I'm going to make a table and a graph. I don't have any shifts that are far away from, well, I don't have any shifts at all, but I don't have any movement away from the origin. I'm going to go for some values of x here. And sometimes you may plug in some values of x and you're like, oh, those really didn't work. I need to pick some different values, and that's okay. You got to play around with it a little bit. I'm going to take my time to plug in each one of those. So you'll probably need some scratch work here. So if I have 3 times 1/2 to the negative 1, 1/2 to the negative 1, when I have a negative in the exponent, I take the reciprocal. The reciprocal of 1/2 is 2. 3 times 2 gives me 6. Plug in 0 for my exponent. Anything to the power of 0 is always 1. So I have 3 times 1, which is 3. One half to the power of 1 is just going to give me 3 times a half, so 3 halves, or 1.5. I'm going to graph this, so I'm going to leave it as a decimal because it's easier for me to plot. Let's see, 1/2 squared is 1/4. Gives me 3/4, and that's 0.75. So looking at my table, I know that my y values have got to go at least up to 6. And then just plot those points. So I'm going to give you just a few seconds. Go ahead and plot those points and see what this graph looks like. It should go down to the right. All right, so this graph actually goes down to the right. But we need to take the time to go through and talk about domain, range, intercept, asymptote, and end behavior. So if you were to compare that to the graph that we graphed previously, make them real small here, you can see the parent function that I did above goes over into the up to the right. That's always going to be what an exponential growth looks like. It's always going to be up to the right, and then an exponential decay should be down to the right. All right, so the domain. As I look to the graph to the left, I could plug in any value I want to over here. I could plug in negative 10 and just get a huge y value, or I could plug in positive 10 and get a teensy tiny y value that's really close to the x-axis. So my domain is going to be the same as before. It's going to be all real numbers. And the range is going to be similar to before. Where does the graph exist vertically? Well, it exists, I can go up forever, but when I come down, I'm going to hit this threshold here, this x-axis, and I can't pass that. So I don't have any negative values for my range. So if I use this set notation, it'll look like that. Whereas the y-intercept, just at 3. Remember, the asymptote is always an equation of a line. At this point in our studies, our asymptotes are mostly y equals some number. This case is no different. My asymptote exists on this x-axis, and the x-axis is the equation of the line y equals 0. And then finally, end behavior. end behavior talks about what happens to the graph as you approach infinity or as you look at the ends of the graph. So I'm going to look at the graph to the left and to the right. So as x goes to the left, as I go to the negative values, if I plug in -1, -2, -3, y shoots up. So as I look to the graph to the left, as x goes to negative infinity, y shoots up to the sky. So in the y direction, we call that positive infinity. I feel like that's really small. Here, write that. And as x goes to positive infinity, so as I look to the graph to the right, this blue part of the graph is going to level off right here. So as x goes to positive infinity, as I look to the bigger values in x, this levels off at y equals 0, which is the asymptote. Last time I wrote the positive x first and then the negative x. Just be aware of that when you're picking, multiple choice answers, which one's which. This time I wrote the negative first. So before moving on to the next example, how is this different than the parent function? So this question doesn't ask this specifically, but let's talk about it. So this function is y equals 3 times 1/2 to the power of x. If I were asked to identify the parent function, the parent function is always just b to the value of x. So what is my b? B in this case is 1/2. So my parent function here would be 1/2 to the power of x. That means 3 is the only transformation. What kind of transformation does this create? Well, if we look above, whenever I multiply by a number in front, it causes a stretch or a shrink. Since 3 is a number larger than 1, this causes a vertical stretch by a factor of 3. It's getting pulled and stretched up. So the 1/2 makes this go down to the right instead of up to the right. The 1/2 makes it go down to the right. It's a vertical, or it's a exponential decay. But the 3 stretches it out. So instead of having an intercept of 1, it has an intercept of 3. It's going to make it taller. So A is an example of a vertical stretch or shrink. B is an example of a translation where I'm actually going to shift the graph. So we'll look at this one as our last example for today. B is equal to 4 to the power of x plus 1, all minus 2. So same thing as before. I'm going to make a table, pick some values of x, and I'm going to plug them in here. So this is where our knowledge of exponents and order of operations are going to be crucial. And I know sometimes just plugging this in and doing this one value can be a struggle. So let's walk through it slowly. So we have 4 to the power of x, and my x value is -2 plus 1, and then all minus 2. So let's see what that gets us. Right, so that's 4 to the -1 minus 2. And that's 1/4 minus 2. I have -2, and if I add a fourth back, I get -1.75. Now, you may need a calculator to help you do that, and that's okay. I'm going to end up erasing this work because I'm going to need the space to do my graph and my talking about my features. So 4 to the power of -1 plus 1, and then all minus 2. I'm just plugging these x values in from my x. Four to the power of -1 plus 1 is 0. Anything to the power of 0 is 1. And I'm going to pause there. I'm going to give you a chance to try to plug in the next 3 numbers. These numbers are going to get big down here, and that's okay. Don't panic if you're like, whoa, that's kind of large. Just give it a try. Take a little practice with exponents. The values that you should have got when you plug in 0 should be 2, and plug in 1 should be 14, and plug in 2, you should get 62. So I'll do the last one. I have 2 plus 1 in the exponent. 2 plus 1 is 3. 4 cubed is 4 times 4 times 4, which is 64. Minus 2 gives me 62. I'm going to erase this work so I've got room for my graph. So if you need any pieces of that, you could jot it down. All right, I'm certainly not going to graph a y value of 62. That's way too big. All right. I know because I have a b value of 4. I have a base of 4. This is an exponential growth, so it should be up to the right. Let's see if my graph reflects that. All right, so negative 2 down 1.5, 1.75. Negative 1, negative 1, 0, 2. And then 114, nope, not going to fit. So I'm just going to guesstimate here. Maybe that could be a little bit more precise. Let's try again. All right, so it doesn't ask me to describe the parent function and the transformations here, but let's talk about it because it doesn't affect how the graph looks, and it gives me some insight into my details of the graph. So the parent function is always just going to be the base of the exponent raised to the power of x. So my parent function is just going to be y equals 4 to the power of x. And then I've got two transformations. I've got the plus 1 and the minus 2. So the plus 1 in the exponent, whatever I do to x always causes a horizontal shift, and it's always backwards from what I think. So if I have the plus 1, that's actually going to be a shift left 1. And then whatever I add or subtract outside the argument is going to be a vertical shift. So the minus 2 is actually going to cause this to go down 2. This down 2 shift right here changes my range and it changes my asymptote. So now my asymptote, instead of being at y equals 0, is now here. It's gone down 2 units. All right, so the domain is going to be unchanged. As I look to the graph to the left, to the right, it still exists everywhere. This is going to be true of all exponential functions that we study in this class. When we look into the range, the graph goes up forever, but it does not go down forever, right? So it goes down, 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 down until I get to the y value of -2, and then I hit an asymptote. That asymptote is the same as where my range ends. So y is greater than -2. It's not or equal to because it doesn't actually touch that asymptote. That value, that range value of -2 is going to be the same as my asymptote value every time. So this is going to be the same as this. Which is also the same as this. Whatever I add or subtract to the end, whatever my vertical shift is going to be that asymptote. So there's a hint for you. It's already in your equation. Now, the intercept you can't really get until you look at the table and you can find it, right? Where is x, 0? What's the y value? Or if you look at the graph. So the intercept is just going to be at 2. And then we'll talk end behavior one more time today. So my end behavior is always going to be what happens to y as I look at x to the left, and what happens to y as I look to x to the right. We haven't seen any so far where the graph is reflected, where it's flipped. As x goes to -infinity, that just means as x goes to the left, right? Where are the small x values? Left, 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 left. What happens vertically? Vertically, does it shoot up, shoot down, or level out? Well, it levels out right here at -2. Y goes to -2. You'll notice that's not a 0. It's the same number for the asymptote and the range. As I go x to the positive values, positive, 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 what happens vertically? It shoots up to positive infinity. So I get a positive infinity over here. All right, that felt like a slow crawl through those notes.